Hello, we will just see what we did in the previous session. We just went through RL circuit, RC circuits, series and parallel in the last session. We saw RL series, RL parallel, and we did not take RLC as a combination of the three elements. Today also we will be continuing with initial conditions to evaluate the current at 0 plus, the derivative and the second derivative of current at 0 plus for different types of examples. So, these things should be at the back of your mind at any point of time. It is at t equal to 0 plus the behavior of the element. For R it is R, at t equal to infinity it is R. Inductor without any initial current acts as open circuit at t equal to 0 plus and he acts as a short circuit. Capacitor without any initial charge behaves like a short circuit, indicating that there is no voltage across the capacitor before and after switching, immediately after switching. At when it reaches steady state, it acts as open circuit. Similarly, an inductor with initial current acts as a current source and a short circuit. A capacitor with initial charge across it will act as a voltage source immediately after switching, and finally it acts as a short circuit. Okay, with this in your mind, and we know the procedure to be followed, the same slide what we saw in the last class, the history of the network. I will just go through this procedure. History of the network is very important at t equal to 0 minus before the switching occurs. Switching action takes place at t equal to 0. Immediately after switching, write the network using the initial conditions. Evaluate the current or the voltage at 0 plus. If it is an inductor, find the current through the inductor. If there is a capacitor, find the voltage across the capacitor. Write the general network after switching. Write the integral differential equation for the general network. Obtain an expression for the first derivative. Using the initial values of I at 0 plus, evaluate di by dt at 0 plus. Obtain expression for the second derivative, d squared I by dt squared, and using the previous values, known values of I at 0 plus, di by dt at 0 plus, evaluate d squared I by dt squared at 0 plus. So, with this we will take up the first problem today on RLC, and we will go ahead with the other problems what I have for today. First and foremost, we will just take up a simple problem on RLC, a DC voltage, a switch, a resistor, an inductor and a capacitor. 10 volts, 10 ohms, 1 Henry, 10 picofarads, 10 picofarad. Let us assume that the switch is closed at t equal to 0. It is a closing switch at t equal to 0. As we know, the first thing is we look at the history of the network at t equal to 0 minus. Here the expectation is find the current at 0 plus, find the derivative of the current di by dt at 0 plus and d squared I by dt squared at 0 plus. So, we need to find what will be the current derivative and its second derivative. So, first thing, as I told you, history of the network at t equal to 0 minus, switch is open, the current through the inductor is 0. I can write that as IL at 0 minus is 0. The voltage across the capacitor at 0 minus is also 0. So, both are zeros, it is relaxed, no charge, there is no current flow. So, both are zeros. At t equal to 0, switching takes place, switch is closed. Immediately after closing the switch at t equal to 0 plus, we need to write the network at t equal to 0 plus. Voltage source, switch is closed, resistor behaves as R, inductor acts as open, capacitor acts as a short. Just look at the table what we saw. This is V, R and R. So, what is the current at 0 plus? Because the inductor, there was no current flowing through the inductor before, it will not allow any current to flow immediately after closing the switch. It does not allow any sudden change in current. With this, I at 0 plus will be 0. Similarly, Vc at 0 plus also is 0. the voltage across the capacitor is also 0 because it does not allow any sudden change in voltage because it acts as a short circuit. So, we have already found one, this is 0. Write integral differential equation, write the general network. The next step is to write the general network after switching R, L and C. Write the general network V, R, L, C. Write the general integral differential equation. V is equal to R into I plus L di by dt plus 1 by C integral I dt. One thing we need to know, what we have written is a Kirchhoff's voltage law for a loop. This is voltage across the resistor, voltage across the inductor, voltage across the capacitor, VL and VR. Obtain an expression for di by dt. Procedure is same for everything. Obtain and rearrange these terms. Di by dt equal to V minus R into I minus, instead of write, okay, 1 by C integral I dt divided by L. We have an expression for di by dt. Substitute the values, known values of I at 0 plus. When it comes to 1 by C integral I dt, it is nothing but the voltage across the capacitor. So, this is nothing but the voltage across the capacitor at 0 plus. This is I at 0 plus. So, if I want to substitute the values at 0 plus, di by dt at 0 plus will be V is 10 minus resistance value is 10, I at 0 plus is 0, voltage across the capacitor is 0, divided by L is 1, this term goes to 0, it is 10 amps per second is di by dt at 0 plus. This is how you need to evaluate. A small change, instead of taking it as 1 by C, it is nothing but a voltage. What you calculate voltage across the capacitor is 0. Substitute that value here, which is nothing but 0. Simplify this with the actual values, you will get the expression or the value of di by dt, it is 10 amps per second. Get an expression for the second derivative. Take this equation, equation A, differentiate this equation, I will get a second derivative term, right. If I take this as Vc, I will get dVc by dt. Instead of that, take it as 1 by C integral I dt and differentiate. So, differentiating this, we get 0 equal to R di by dt plus L d squared I by dt squared plus I by C. Obtain expression for the second derivative, d squared I by dt squared equal to minus R by L di by dt minus I by LC. If you want to know, evaluate the current at t equal to 0 plus, substitute the known values of I at 0 plus, di by dt at 0 plus, what we have, and evaluate d squared I by dt squared at 0 plus. D squared I by dt squared at 0 plus will be minus 10 by 1, di by dt at 0 plus is 10 minus I at 0 plus is 0 by L into C, the whole term goes to 0. So, it will be minus 100 amps per second squared. In this case, in all the previous cases what we saw, your final state of your capacitor is open, initial state is a short, final state of inductor is short, initial state at t equal to 0 plus, if there is no current flow, is an open circuit. Just for our reference, let us see at t equal to infinity, this particular circuit behaves this way. I have R, L acts as a short, capacitor acts as open. Current at infinity will be 0 in this. That means the current starts from 0. Why I am telling you this is, if I just want to plot the current with respect to time, in case of an RLC series circuit, I need to have an idea about what will be the current at infinity. Because the presence of the capacitor, here the current goes to 0. Initially it starts at 0. Initially the current starts at 0. There will be no current before. It has a positive slope. Gradually it reduces. In all the previous cases, it used to settle down at that place. In this case, the current will somehow come back to 0 because of the presence of an element C in the circuit. So, this is how a current will be in case of a RLC network. So, with this introduction we will go to the next problem, because we have covered RL series, RL parallel, RC series, RC parallel, and a combination of RLC series. Okay. We will take the next problem. The network shown, we will just try to evaluate I di by dt, d squared I by dt squared. The difference between the problems what we took in the previous session and this session is, we have two positions A and B. Till now we had only one, either the switch was closed or open. Either in a parallel circuit we saw that the switch was a opening switch, whereas in a series circuit we saw that the switch was a closing switch. In this case, in the problem says the network shown, switch K is changed from position A to B at t equal to 0. We need to see what happens once the switch changes from A to B, but we should now understand what will be the status of the circuit when the switch is in position A. When the switch is in position A, that means if this is in position A before the switch is closed, the circuit has already undergone a transient. Long back the switch was changed to A, it was moved to A, and it has reached a steady state. I mean to say, the question here is to find I di by dt and d squared I by dt squared once the switch is moved from A to B. But right now the switch is already at position A and a steady state has been established already. Because this is the first type of problem we are taking in this with two states A and B. The switch can be either put to A or put to B. So, at position A we need to analyze this step by step. At position A already the circuit has reached a steady state that has been given in the problem. I will just take down the same problem. It has two positions A and B where capacitor is connected to B, switch, I have a R and I have a L connected to this, and the switch is already in position A. This is position A and position B with a voltage source. The value of voltage is 100 volts, the value of resistor is 1000 ohms, and the value of inductance is 1 Henry. 1 Henry and 1 microfarad capacitance. So, when it is already at position A and steady state have been established, means the first is the history of the network. We need to understand the history of the network at t equal to 0 minus. Now, for me 0 minus before the switch is moved to B, 0 minus is the switch is at A and a steady state has been established. Means my circuit, actual circuit will be, the switch is at A, R behaves as R, transients have gone, resistance behaves as resistance, inductor's final state in this case will be a short circuit. This is the change, right. Inductor acts as a short circuit, it is the value of resistance and V, and there will be a current flow at t equal to 0 minus. This is a typical case of a current through an inductor before the switching action takes place. When it is at position A, anyway it does not matter whether I connect a capacitor here or not, because this at B there is no connection to this. Now, once the position, in this case what will be the current at 0 minus? Current at 0 minus will be V by R. V by R is 0.1 amperes, 100 divided by 1000 will be 0.1 amperes I 0 minus. What will be the voltage across the capacitor at 0 minus? 0. Whenever there is an inductor, find the current through the inductor, whenever there is a capacitor, find the current through the capacitor and leave it at that point. It might help us in understanding the circuit. At 0 minus, it has reached a steady state, inductor is acting as a short circuit, but there is a current through the inductor. At t equal to 0, switch is moved from A to B. At t equal to 0, write the network at t equal to 0 plus. Immediately after, this is the next step what we have to follow for evaluating I and di by dt, d squared I by dt squared. At t equal to 0 plus, if I write the network, switch is moved to B, R behaves as R. You just look at the table. I will just go back once to the table. Okay. With the general network after switching, we see that if there is a current through the inductor, it acts as a current source, and finally it acts as a short. Till now we have not taken any problem like this. This is the case of an inductor with initial current and capacitor without any charge across it before the switching action. So, it acts as a short circuit here in this case. So, if you want to write the network at t equal to 0 plus, capacitor acts as a short, resistor acts as R, your inductor, because of the initial current, it acts as a current source whose value is 0.1 amperes. This is the state only at t equal to 0 plus. So, in this loop, I at 0 plus will be 0.1 amperes. Your inductor does not allow any sudden change in current. This is the reason why the current after switching and before switching remains the same in all the problems. So, now write the general network after switching. General network is the switch is moved to B, this is your position B, R, L and a C. A loop equation, we get 0, there is no forcing function, R into I plus L di by dt plus 1 by C integral I dt. The voltage across the capacitor at 0 plus is also 0 because it is initially relaxed. There is no voltage across the capacitor. This is the voltage across your capacitor Vc. Get an expression for di by dt. Di by dt at 0 plus will be minus R by L into I at 0 plus minus Vc at 0 plus by L. This is nothing but the voltage across the capacitor, voltage across the inductor, voltage across the resistor, all put together in a loop. The total voltage has to be 0 because there is no forcing function. So, get an expression for di by dt, substitute the values of I at 0 plus, Vc at 0 plus, voltage across Vc at 0 plus is 0, this goes to 0, I at 0 plus is 0.1. So, di by dt is minus 1000 into 0.1 divided by 1, it will be minus 100 amperes per second. So, I at 0 plus will be 0.1 amperes, di by dt at 0 plus will be minus 100 amps per second. If I want the second derivative, differentiate this equation, obtain an expression, substitute the values, known values of I at 0 plus, di by dt at 0 plus and get a value for d squared I by dt squared at 0 plus. So, differentiating this, we get 0 equal to, differentiating the equation again, general equation, we get R di by dt plus L d squared I by dt squared plus I by C. Obtain expression for d squared I by dt squared. D squared I by dt squared will be minus R by L di by dt minus I by LC. At 0 plus, just substitute the values, minus 1000 divided by 1, di by dt at 0 plus is minus 100 amps per second, minus I at 0 plus is 0.1, L is 1, C is 1 microfarad, 1 into 10 to the power of minus 6. If you just see, this will be plus 10 to the power of 5, this will be minus 10 to the power of 5, finally this results with a 0 value. So, the second derivative, the slope at which the current changes is 0. This indicates d squared I by dt squared at 0 plus is 0. Indicates that if I just want to plot the current through this loop in a RLC circuit, once the switch is moved from A to B at t equal to 0, the current starts from a value 0.1, it has a negative slope and the slope does not change. This tells how the slope is going to change. The slope does not change, it directly comes to 0 and stops. So, this will be the curve what the current takes. It is not an exponentially decaying, it is a linear decaying curve. So, the current linearly comes to 0 because this is a second derivative is 0, indicating there is no change in the slope. It is negative, it comes to 0 with time. Right. So, we will go to another problem. Okay. This is another problem what we will see today. Normally in most of the exams they have asked this problem. This is a very standard problem. It says in the network shown in figure, we have two positions of a switch. It is a SPDT switch, single pole double throw switch. Same question as in the previous case. The network is already connected and the switch is at position A, and when it moves from A to B, we need to show that the value of I1 at 0 plus and I2 at 0 plus is equal to minus V divided by R1 plus R2 plus R3, and I3 at 0 plus is 0. We do not have to find the derivatives of I1, I2, I3 whatever. The problem is very simple, but only thing is we need to understand and analyze the circuit. The circuit given, just see the circuit here. The switch is at position A at t equal to position A, steady state has been established. When a steady state has been established, I will just write the circuit first and then we will go through the other things later on. R2 L1 R1 L1, I have a resistance R1 here, R1, this is R2, this is C3, L1, L2, L1, L2, R3, C1, C2. This is the network given, and the currents are, the loop currents says I1, I2 and I3. And the problem states that in the network shown, the switch K is changed from position A to B and steady state has been established when the switch is at position A. Means if I just look at the history of the network, at t equal to 0 minus, the switch is in position A, Here what we need to do is we need to take their steady state values or t equal to infinity. Already a transition has, it has gone through a transition. Your capacitor acts as an open. We just see the tables, what we are, no, capacitor acts as open, the final state of the capacitor is open, inductor acts as a short R behaves as R at t equal to infinity, capacitor acts as open, this inductor acts as a short, capacitor C3 acts as an open, and at B I have one resistor R1. This is V, this is your capacitor C3, this is your inductor L1, this is your R3, L2, C2, C1. These are the final states of your inductors and capacitors at t equal to 0 minus, because already it is at position A, the switch is in position A and a steady state has been established already. So, you need to represent the previous state as there, as the transients have, it has gone through a transient, it has reached a steady state. Now, let us see what will be the current through each loop. What will be I1, what will be I2, what will be I3. I1 is 0, I2 at 0 plus, I3 at 0 plus is 0. This is the network at t equal to 0 minus. So, I1 at 0 minus, I2 at 0 minus, I3 at 0 minus, all are zeros. For curiosity, let us see what is the voltage across the capacitors. I told you whenever we have inductors and capacitors, we will just try to find the voltage across the capacitor and current through the inductors. We already found the current through the inductors, because the current through L1 is I1 difference I2, right, current through L2 is I3, we have found all the three currents. What about the voltage across your capacitor? Voltage across your capacitor C1, voltage across your capacitor C2 at 0 minus before the switching, voltage across the capacitor C3 at 0 minus. What will be the voltage across your capacitor C1 at 0 minus? If you just take, this is the voltage which is nothing but the voltage across this short. There is no current, there is no voltage drop here. The voltage across C1 is nothing but the voltage across your inductor L1, which is nothing but 0. So, voltage across your capacitor C1 is 0. Voltage across your C2 is also 0, because this voltage is nothing but the voltage across this short, and inductor is also 0, but the voltage across your capacitor C3, this would have charged to a value, because this exactly is nothing but a voltage V. The capacitor C3 has a, would have charged to a value V when it is at position A. So, this will be V volts, which is nothing but your supply voltage V. Okay. This voltage is nothing but the voltage your supply, DC supply voltage. This capacitor would have charged with this plate positive and this plate negative with the value V, which is equal to your supply voltage. So, this will be your previous history. This helps us in understanding the next state after switching. So, that is why history becomes very important. The current, previous value of the current at I1, I2, I3 are all zeros, because all are open circuit. Voltage across this is nothing but the voltage across the short, it is 0. Voltage across C2 is nothing but voltage here. Voltage across C3 is nothing but the supply voltage. This helps us in writing the network at t equal to 0 plus. So, this is the history. At t equal to 0 plus, the switch is moved to B. At t equal to 0 plus, switch is moved to position B. We need to write the network at t equal to 0 plus. Network at t equal to 0 plus. At t equal to 0, the switch is moved. Write the network at t equal to 0 plus means when the switch is moved to B, I have a resistor which gets included, that is R1. The capacitor with initial charge acts as a voltage source. We have seen that. We have a capacitor C3 with a charge across it, and it acts as a voltage source with this end positive and this end negative. This acts as a voltage source V at t equal to 0 plus. There was no current through the inductor. This inductor L1 acts as open. this resistor R3 behaves as a resistor, capacitor across, the voltage across the capacitor was 0, so it acts as a short, there was no voltage across C1, it will not allow any change in voltage immediately. Similarly, the current through the inductor was 0, it acts as open, the voltage across C2 was 0, so it acts as a short. Finally, this will be the network, this was I1 assumed, this was I2, this was I3, we have a resistor R2 here, R2, a resistor R2 in the circuit, this resistor will be R1, R2, this will be your R3. If you just see the network at t equal to 0 plus, the current I3 will be 0, I3 at 0 plus, I3 at 0 plus is 0. Immediately after the switch is moved from A to B, this I3 will be 0. What will be the current for I1 and I2? This will not allow any sudden change. There is only one current flow in this loop, there is only one loop. The resultant loop is the current flows in this resultant loop in the opposite direction to the assumed direction of I1 and I2. Therefore, I can say I1 equal to I2 equal to minus, this minus sign is just because the assumed direction of I1 and I2 are clockwise and this capacitor drives the current in the opposite direction, therefore, it is negative, and the current which flows in the closed loop is V by R1 plus R2 plus R3. So, it is nothing but V divided by R1 plus R2 plus R3. The question was this, just show that I3 is 0, I1 and I2 is minus V by R1 plus R2 plus R3. If we just see the question, they have asked you to show I1 at 0, I3 at 0 plus is 0 and I1, I2 is V divided by R1 minus V divided by R1 plus R2 plus R3 is what we obtained. So, the network at t equal to 0 minus becomes so important for us to analyze the network at t equal to 0 plus. Right. So, this problem has appeared many times in the examination, please be careful, go through this again. We will go to another network today, we will go to the next problem. Here, if we just see the problem first, before getting into the problem, we will see what the problem says. It says steady state is reached when switch K is open. The switch now, we have transition and steady state, any element changes, there is a introduction of your voltage source into the network, a current source into the network or a removal of any element, there will be a transition, there will be a steady state. In this case, the switch is initially open and steady state has been established. He says the switch is initially open, means K is open and switch is closed at t equal to 0. So, we need to know what is the status of the switch before the operation. So, initially the switch is open means the resistance R1 is included in the network at t equal to 0 minus. So, once the switch is closed, the resistance becomes redundant because it bypasses, it is a switch which acts as a short circuit across the resistor. So, we can see that steady state is reached when the switch K is open. We need to know the history of the network and he has asked you to find V naught, the voltage across capacitor and indicate the polarities. There is only one capacitor in the network. So, we will find out all these things today. I have a voltage source, a resistor and a RL and a RC. It is RL and a RC network. This is RL, RC with R. we call this as R1, R2, R3, R1, R2, R3, and there is a switch here. Switch is initially open. When the switch is open, means this resistor is included, it has reached steady state. So, we need to see what are the current through I1 and I2, and here is very specific. He has given the branch currents I1 and he specifies this is I2. We just see at t equal to 0 minus, at t equal to 0 minus, switch is open, when the switch is open, this is V, voltage is 100 volts, R1 10, R2, R3 20, 10 ohms, 20 ohms, 20 ohms, inductor is 1 Henry 1 microfarad, 1 Henry 1 microfarad. So, when the switch is open, R is included, circuit has reached a steady state, inductor acts as a short circuit, the final state, R3, capacitor acts as a open circuit. At t equal to 0 minus, this is the history of the network, because I need to analyze after the switch is closed. The switch is closed at t equal to 0. So, this is 10 ohms, 20 ohms, 20 ohms, and the voltage is 100. There will be a current through this branch, I1 will be flowing, I2 will be 0, because your capacitor acts is open. The question here is, what is the voltage across the capacitor? V0, and indicate the polarities before the switch is closed. So, there will be a current, there will be a current through this loop. So, this current I will be 100 divided by 10 plus 20, 30 will be 3.33 amperes. Current I1, I can call this as I1 at 0 minus, I2 at 0 minus will be 0, right. Means what will be the voltage across the capacitor? This voltage across the capacitor will be nothing but the voltage across this branch. Current is 0, the drop across this is 0, but this capacitor will have a voltage which is equal to the voltage across this. There is a current flowing through this, right, and this capacitor voltage will not be 0. This voltage, because it acts as open, it will be nothing but the voltage across your 20 ohms. So, Vc at 0 minus will be I1 into R2, it will be I1 R2, I1 into R2, which is 3.33 into 20 is 66.67 with polarities as shown. This will be having a negative polarity. So, this is your capacitor C, this is your inductor L. Voltage across your capacitor will be 66.67 volts with polarity as indicated. So, that is how we get 66.67 volts with the polarities indicated as shown. Now, when there is a transition, that means whether you remove any element, whether you connect a supply to the network, there will be a transition, there will be a steady state. The currents are going to change, because I am going to, by closing the switch across the resistor R1, resistor R1 becomes redundant. Now, the circuit parameters have changed. We need to evaluate different values of current I1 and I2 through the network. So, initial values of I1 and I2, Ti1 by dt at t equal to 0 plus, we need to see after the switch is closed. So, this is one part. This is the history of the network. We have seen that the current through this is 3.33, current through this is 0, but there is a voltage across the capacitor which is nothing but the voltage across this parallel branch. The current through this is 0, voltage drop across 20 ohms is 0, the voltage across capacitor is 66.67. Now, the switch is closed at t equal to 0. At t equal to 0, the switch is closed, the resistor becomes redundant, voltage, the switch is closed, this resistor becomes redundant whether I write it or not, because the resistor across the switch effectively it acts as 0. Switch is a short circuit. I have R there was a current through the inductor. The inductor with initial current acts as a current source. So, this acts as 3.33 amperes initial current I naught or I at 0 minus. It does not allow any sudden change in current. I have a resistor. This is a case of a capacitor with initial voltage. So, he acts as a voltage source with polarities 66.67 volts. This is 20 ohms, this is 100 volts. So, if you want to know what is I1 at 0 plus, if this is I1, this is I2, I1 at 0 plus is 3.33 amps only, because the inductor, it does not allow any sudden change in current, the current remains the same at 3.33 amperes. The current I2 at 0 plus will be, just let us look at this loop, the outer loop, 100 volts, 66.67 volts. If I write a loop equation for the outer loop, if I write a loop equation for this outer loop, right, it will be 100 minus 66.67 divided by 20 will be your I2. So, I2 is 33.33 by 20, which works out to be 1.67 amperes, 1.67 amperes, I2 at 0 plus. So, we have found out I1 and I2 at 0 plus after the switching, and we have to evaluate dI1 by dt, d squared I1 by dt squared. We have seen voltage across the capacitor, which is nothing but 66.7 volts. The polarities are plus and minus across this. We saw I1 at 0 plus, I2 at 0 plus, which are nothing but 3.33 and 1.67 amperes. Now, we need to see what is dI1, what is dI2 by dt at t equal to 0 plus after switching, and the last one is di by dt at t equal to infinity. So, we need to write a loop equation, a general network after switching. This switch R, L, R, C. So, this is my current I1, this is my current I2, this can be one loop and this can be the other loop. I can write two loop equations for this. So, the first loop equation is for I1, this is I2, this is the total current I1 plus I2, right. If there is any resistor, I should have taken this as I1 plus I2 as the current through this. It is nothing but V for the first loop, V is equal to R2 I1 plus L dI1 by dt. This is R2, this is R3, whose values are 20 and 20 ohms. So, if I want to find dI1 by dt equal to, just rearrange this, V minus R2 I1 by L, V by R2 I1 by L. So, at t equal to 0 plus, find the value of dI1 by dt, it is 100, V is 100 minus 20, I1 at 0 plus is 3.33 amperes divided by L is 1 Henry. So, it will be 33.4 amperes per second. This is 100 minus 66.66 is 33.33 amperes per second is dI1 by dt at 0 plus. I need to find dI2 by dt. So, you write a loop equation for the second loop, this is your I2. For the loop 2, it is V is equal to R3 I2 plus 1 by C integral I dt. To get dI2 by dt, I need to differentiate this equation. So, I call this as equation A and B. Differentiate equation B to get dI2 by dt. So, when I differentiate this equation, I get 0 equal to R3 dI2 by dt plus this call it as I2 by C. Substitute the values of I2 at 0 plus, I have value of I2 at 0 plus as 1.67 to get dI2 by dt. So, dI2 by dt at 0 plus will be minus I2 at 0 plus by R3C. So, if you evaluate, we will get this as, if you just substitute I2 as 1.67 divided by R3 is 20 into C is 1 microfarad, 1 into 10 to the power of minus 6, we get di2 by dt equal to minus, because I have a minus sign here, 83,500. So, we have obtained di1 by dt, di2 by dt, and the values are 33.4, 83,500 negative. The last part here is find di by dt at t equal to infinity. So, at infinity, if I just want to always keep a tab on what will be the current at t equal to infinity. At t equal to infinity, switch R inductor acts as a short, R capacitor acts as open. If this is I1, this is I2, I1 at infinity is 100 by 20 is 5 amperes, I2 at infinity is 0. This capacitor voltage Vc will be 100 volts, because this nothing but the voltage across this. The capacitor would have charged to a value of 100 volts because the supply, and the current through the inductor will be 5 amperes, but in the question they have asked what is di1 by dt at infinity. At infinity there is no rate of change of current, the current through I1 remains 5. So, di1 by dt at infinity means, if you want, di1 by dt at infinity will be 0, because there is no change in current, the current in this loop is 5 amperes only, there is no change in current at infinity. So, you have got this di by dt as 0. This is, in fact, this should have been di1 by dt at infinity, because we have I2 also. I2 at infinity is 0, I1 at infinity is 5 amperes. So, di by dt is 0. So, we have gone through. In the next class, we will just get into transient analysis, how your initial conditions are going to help you in evaluating the arbitrary constants will be explained in the next class, with 1 or 2 more problems on the initial conditions. We will take up 2 typical problems in the next session, and we will go through the transient analysis on DC circuits and RL, RC again. DC applied to RL and RC, we will see an expression for current with respect to time. It is not I at 0 plus. Anyway, all these things are going to help us in evaluating the arbitrary constants of a differential equation. Thank you.